My dear students of ELEC 342, welcome to this lecture that will cover the eventuality of transit not being operating this coming Tuesday. It's about the parallel operation of transformers and generators. Normally we begin with a customer that has a very modest power requirements when he or she contracts for service, right? And then we use a matching transformer and matching generator. But as the customer needs grows, we will need to match the power requirements. What do? We do replace the transformer and the generator with bigger ones, or we connect new ones in parallel. In parallel, sure. The best solution, the economic solution, is to connect the second unit in parallel with the old one. But we have to make sure that this can be done, that there's compatibility between the existing unit and the new one. Let's explore the conditions for compatibility for transformers first, and then for generators. We remember in three-phase systems that we can transform the generators and the loads to Ys. Well, assuming there is symmetry and balance, of course, that we do. And then we solve only the phase A to neutral circuit. Remember that. A single phase, a Y of a three-phase transformer. We have seen ideal transformers and the representation of a single-phase transformer. We have seen that. But how do we include the phase shift between the primary and the secondary in a three-phase clock connection? Let's see how. There is a phase shift between the neutral to phase A voltage in phase in the primary and the neutral to phase A in the secondary, and it's given by the clock number. We know that. As an example, in a dy5, there's a phase shift of 150 degrees between the neutral to phase A in the primary and the neutral to phase A in the secondary. Let's work with a yd5, the mirror of the first one. This is the primary. That is a neutral to phase A of the primary. This is a secondary in delta, and that is phase A2. And this is a neutral to phase A of the secondary. Right. Those are the physical windings. But the ratio that we're interested in when we find a Y equivalent circuit in a three-phase of a clock connection of the transformer is between those two vectors, between those two phasors, NA1 and NA2. VNA2 is lagging behind VNA01 by 5 times 30 by 150 degrees. The model that we have learned is either this one or that one if we neglect the magnetization and the excitation current altogether. Let's consider that we have a YD5 connecting a 34 kilovolt system to a 230 kilovolt system. Remember, I'm talking of line-to-line voltages, of course. This is a three-phase system talk. The actual single-phase transformer ratio will be between the primary and the secondary, the physical primary and the physical secondary of each one of the three-phase transformer is given by those windings would be between 34 over root 3 kilovolts and 230 kilovolts. That is the ratio of each one of the physical single-phase transformers. But that is not what we need, not at all. What we need for the equivalent single-phase transformer is a ratio between this voltage and this one here. Between 34 divided by root 3 and what is this? 230 divided by root 3. That is a ratio that we want for the single-phase transformer that will represent that combination in a three-phase one-line diagram, 6.765. And of course, we need to include the negative 150 degrees phase shift. This is the model. Neutral to phase A of the primary, neutral to phase A of the secondary. And the ratio, 1 to 6.765. And of course, the phase shift. negative 150 degrees when we move from the primary to the secondary. Or we add if we're moving to the primary. Both for voltages and currents jumping from primary to secondary. Let's say that secondary voltage is known to be 125 kilovolts with 15 degrees. What is the voltage here? You say, well, that voltage is 125 divided by 6.765. And the phase shift? Is it 15 degrees? No, it is not 15 degrees. Of course, it's 15 degrees plus 150. That is the right voltage there. 18.48 kilovolts with 165 degrees. What about currents? If the current here is known to be 13.5 amps with negative 10 degrees, the current on the primary side would be 6.7 times bigger, 91 amps, but with a phase that is also 150 degrees more. This is done so that the power factor is not changed. Now, to connect two transformers in parallel, we have to ensure that they have the same transformation ratio. Why? That they have the same connection clock number. Why? And that both have the same short circuit impedance in per unit. Why really? We have to find out why. The same transformation ratio, that kind of makes sense. Let's connect two transformers in parallel, or rather the single phase equivalents, this one and that one. We connect them in primary in parallel, and we connect them in parallel in the secondary as well. Now we know the ratio A1 and A2 for each one of those transformers, the single phase ratios, right? And we know the clock numbers for the first transformer and the second transformer. And now we apply the same voltage V1 to the primaries of both of them. Then E1 and E2 can be computed from V1, from G1, A1, G2, and A2. This way, the magnitude of A1 will be V1 divided by A1. Absolutely. What about the phase? The phase will be the phase of E1 minus 30 times the clock number of the group 1, G1. And that is the voltage E1. And the voltage E2? The voltage E2 has this magnitude and it has this phase. Nice. Let's concentrate now on the secondaries. Right? We know the voltages. We have that circuit for the secondaries. Let's trim the secondary. Let's stretch it like so. Long. It is the same circuit, right? There we see that if there is no load and D1 is not equal to E2, there's going to be a circulatory current with parasitic losses that we do not care for. Do not confuse the term parasitic in this context with the one we used in the core. No, this is not about eddy currents. It is about a current that circulates in that connection loop. We don't want that. For that reason, to eliminate that circulatory current, we have to make sure that E1 is equal to E2. Otherwise, we have a current, an undesirable current circulating between the transformers. One of the transformers is feeding the other one. We don't want that. E1 has to be equal to E2 in magnitude and in phase. This is E1, this is E2. Well, it is necessary, of course, that the ratios A1 and A2 are the same, and also that the clock groups are the same, right? And that deals with the first two conditions. For a transformer to be connected in parallel with another, we have to make sure they have the same transformation ratio, and they belong to the same clock number. What else? They have to have the same short circuit impedance in per unit, not in ohms. Why? Let's see. Let's refresh on per unit. How do we compute the base ohms? We start the base power and base volts. And then we compute the base amps like this one, right? And then we can compute the base ohms this way. Or this way, which is the favorite for electrical engineers. The base ohms, the base amps. Fine. We know that A1 is equal to A2. So that condition, or those two conditions, have been met. So we can say that the point above E1 and above E2, they are at the same electric potential. We can join them together like that. It is the same. It is the same, right? Now let's see what are the conditions for Z1 and Z2. That is the current in the load. The current in the load, that is the current supplied by transformer 1 and the current supplied by transformer 2. We have a current divider, of course. I load is divided between Z1 and Z2 this way. That is the ratio between the two, right? And this is the current in the second transformer. If we find the ratio of them, we see the load is divided between the two transformers according to their short circuit impedances. And that, of course, is expected. But what we want really is that they divide the current according to their power rating, so that the bigger transformer supplies the bigger current and the bigger power contribution. One thing is what we have. I1 over I2 is Z2 over Z1. And another is what we want. We want that the two currents are related as the power ratings of the two transformers. Let's see how we achieve that. How do we achieve that? We want to achieve this, I've said, right? But what we have is that they split according to the impedances. Let's go from what we have to what we want. This is what we have. We can write Z2 and Z1 in terms of the per unit values and the base voltage and the base powers of the transformers. Correct. This cancels that because V base is the same for both transformers. Right. What we want is that, right? We want that ratio is that. How do we achieve that? Making sure that Z1 per unit is equal to Z2 per unit. And then it will be true that I1 is to I2 as S-rated 1 is to S-rated 2. That is a condition. And that is what we wanted to demonstrate. To connect two transformers in parallel, they have to have the same ratio. They have to belong to the same clock group. And in per unit, they must have the same short circuit impedance. The three conditions need to be met. And generators, for generators, we connect the armatures of two generators, or rather, we connect the neutral to phase A equivalents of the armature of the two generators and connect them in parallel. E1 is equal to E2. Why is that? Well, the generator is rotating at the same speed. E1 and E2, they have the same frequency. Also, we make it so that they are in parallel. Otherwise, you make it so that they have the same phase. Otherwise, there would be a circulatory current. So we force that E1 is E2. So manipulating both the power of the prime mover, of the mechanical prime mover, so to control the shift, the phase shift, and we control the current in the field to control the magnitude and make sure that they match. And then they have the same RMS and the same frequency and the same phase. Fine. In per unit, they must have the same Z as well. So they split the load according to their relative rated powers. The same deal. The maximum total power that can be fed would be then the sum of the rated power of each one of the transformers. And that is the end, my students. I hope you spend the rest of the week profitably. I'll see you in the final exam.